For most of the world, power is visible. Fighter jets flying overhead, aircraft carriers cutting through oceans, skyscrapers rising above cities. But the most powerful machine America has ever built does not fly, sail, or explode. It sits quietly behind concrete walls, buried beneath layers of security, operating in silence. No crowds watch it. No headlines celebrate it. Yet this machine has the ability to recreate the conditions of stars, simulate nuclear explosions without detonating bombs, and influence the global balance of power. This machine does not look powerful. There are no flames, no shockwaves, no dramatic countdowns. And that is exactly why it is so dangerous and so important. For decades, America built this machine away from public attention. Not because it was illegal, not because it was unethical, but because understanding its true purpose would reveal how modern power really works. This is the story of how America secretly built one of the most powerful machines in human history. Why this machine had to exist. After World War II, the United States entered an era where survival depended on knowledge rather than brute force. Nuclear weapons had changed everything. A single detonation could erase a city. But detonations came with consequences. Radioactive fallout, political backlash, environmental destruction, and international treaties. By the late 20th century, nuclear testing was no longer an option. Treaties banned underground explosions. Public pressure mounted. Environmental damage became impossible to ignore. But here was the problem. Nuclear weapons still existed, and ignoring them did not make them disappear. America faced a terrifying dilemma. How do you maintain nuclear capability without testing nuclear bombs? How do you understand weapons you are no longer allowed to explode? How do you ensure reliability, safety, and deterrence without ever pulling the trigger? Computers were not enough. Simulations alone could not fully model nuclear physics. The forces involved were simply too extreme. So the United States decided to do something radical. Instead of exploding weapons, it would recreate the physics of explosions. A concept that sounded impossible. The idea was almost science fiction. If nuclear explosions could not be tested, then the conditions of nuclear explosions would be manufactured artificially in controlled environments for fractions of a second, using pure energy instead of bombs. This meant recreating temperatures hotter than the surface of the sun, pressures greater than Earth's core energy densities that normally exist only in stars, and doing it safely, repeatedly, without destroying the facility. No machine in the world could do this. So, America built one. A machine that uses light as a weapon. At the heart of this system lies an idea so simple it hides its complexity. Light. Not ordinary light, but laser light amplified to absurd levels. Instead of one beam, the machine uses hundreds of synchronized laser beams, each one traveling through a precisely engineered path. Every beam must arrive at the target at the exact same moment. Even a delay of a billionth of a second would ruin the experiment. Each laser pulse begins weak, harmless. But as it travels through the system, it is amplified again and again inside massive chambers filled with specially designed crystals. These crystals do not amplify light on their own. They must first be charged using enormous electrical systems that store energy for hours, just to release it all in one instant. When the system fires, it consumes more electricity than thousands of homes combined. All that energy, released in less than a second. Engineering at the edge of physics, the machine is not one device. It is a system of systems. Power delivery networks capable of handling extreme surges. Cooling systems preventing components from melting. Optical paths kilometers long that must remain perfectly aligned. Control software coordinating thousands of operations simultaneously. Even temperature changes of a fraction of a degree can cause materials to expand or contract enough to misalign the lasers. To prevent this, the facility is climate controlled at levels far beyond ordinary buildings. Vibrations from nearby traffic, footsteps, or even distant seismic activity could interfere with alignment. That is why certain areas are restricted during operations. Silence is not a preference here. It is a requirement. The target smaller than a grain of pepper, all this power is aimed at something shockingly small. A target roughly the size of a peppercorn. Inside that tiny capsule is fuel, often isotopes of hydrogen. When the lasers strike, The target is compressed evenly from all sides. In less than a billionth of a second, pressure and temperature skyrocket. For a brief moment, the laws of normal matter collapse. Atoms are stripped apart. Plasma forms. Fusion reactions ignite. This is not an explosion, but it is close enough to reveal everything scientists need to know. In that moment, the machine becomes more powerful than any weapon ever deployed, yet leaves no crater behind. Why this machine changed everything with this system. America could finally do what no other nation could reliably achieve. Study nuclear reactions without nuclear detonations. Maintain deterrence without breaking treaties. Test materials under extreme conditions. Advance fusion energy research. This machine became the backbone of America's nuclear stewardship program, ensuring weapons remained safe, reliable, and controlled without ever being used. At the same time, it opened the door to something far bigger: fusion energy. The same reactions, powering the sun. If mastered, fusion could provide nearly limitless clean energy. And this machine is one of the few tools capable of studying it under real conditions. Failures, setbacks, and billions lost building this machine was not smooth. Early tests destroyed components worth millions of dollars in a single shot. Optical elements shattered. Sensors failed. Materials vaporized under energy levels engineers had never dealt with before. Each failure revealed new problems and forced new innovations. New types of glass had to be invented. New polishing techniques at nanometer precision were developed. New radiation-resistant electronics were created. Entire industries emerged just to support this one system. YT was kept secret. This machine represents knowledge dominant. Anyone who understands how to build it gains nuclear simulation capability, fusion, research, leadership. Extreme physics mastery. Revealing too much would allow others to replicate it, and replication would mean a shift in global power. That is why, for years, this machine operated in near silence. The machine behind the machine. The most dangerous thing about this machine is not its power, it is its control. Power without control is chaos. Control without power is useless. What America built was a system that mastered both. At scale, no human being can directly operate the machine. There are simply too many variables. Temperatures change. Materials expand. Electrical loads spike. Optical paths drift by decisions must be made in microseconds. Human reaction time is far too slow. So the machine was designed to operate under a layered control architecture. A hierarchy of automation, software intelligence, and human oversight. Every laser pulse is planned days or even weeks in advance, but its execution happens almost entirely without human touch. At the lowest level, thousands of sensors monitor pressure, temperature, vibration, voltage, alignment, and radiation in real time. These sensors feed data into control systems that continuously adjust mirrors, lenses, and power delivery paths. The system never waits for commands. It reacts automatically, correcting itself faster than any operator could even notice a problem. Above this layer sits a supervisory control system, a digital brain coordinating everything. It ensures that no subsystem fires unless every other subsystem confirms readiness. If even one parameter drifts outside tolerance, the entire operation aborts instantly. Not slowly, not partially. Instantly. This is not safety theater. At these energy levels, hesitation means destruction. Why ordinate engineering could not work? Traditional engineering principles break down at this scale. Materials behave differently under extreme radiation. Electronics fail unpredictably. Heat does not dissipate normally. Even air becomes a problem, as tiny density changes can distort laser paths. To solve it, these engineers were forced to rethink almost everything. Optical components had to be manufactured with surface smoothness measured in nanometers. Any imperfection would scatter light, destroying the beam's coherence. Mirrors were polished using custom-built machines operating in vibration-isolated rooms. Even the polishing compounds had to be reinvented to avoid microscopic contamination. Glass production itself became a bottleneck. The machine required enormous slabs of ultra-pure glass, free from bubbles, impurities, or internal stress. No existing manufacturer could meet the requirements. Entire production lines were redesigned just to produce acceptable material. And then there was the issue of alignment. Keeping hundreds of laser beams perfectly aligned over long distances is like threading needles from kilometers away, simultaneously, while the needles are moving. To achieve this, the system uses automated alignment tools that continuously adjust mirror positions using feedback from diagnostic lasers. The alignment process never stops, even when the machine is idle. The role of supercomputers: every experiment produces massive amounts of data. In a single pulse, the machine can generate terabytes of information: pressure curves, temperature maps, radiation signatures, and plasma behavior data. This information must be captured, stored, and analyzed almost instantly. Supercomputers play a critical role here. Before a shot is fired, simulations are run to predict outcomes. These simulations model atomic interactions, energy flow, and material behavior under conditions that cannot be tested elsewhere. After the shot, real data is compared to predictions. Differences reveal new physics or flaws in assumptions. This feedback loop is what allows the machine to evolve. Without supercomputing, the machine would be blind, and without the machine, the simulations would be guesswork. Together, they form a closed system of knowledge generation that no single component could achieve alone. Failure is part of the design. Unlike consumer technology, failure was expected here. In fact, it was planned, for engineers knew that early operations would destroy components, that sensors would saturate, that optical coatings would burn off. Instead of trying to prevent all failures, they designed systems that could fail safely and predictably. Components are modular. Damaged sections can be isolated and replaced without dismantling the entire machine. Critical systems are redundant. If one pathway fails, another takes over instantly. This philosophy allowed rapid learning. Each failure taught engineers something new about extreme physics. Each destroyed component pushed material science forward. Many of today's advanced manufacturing techniques were born from these failures. Why this machine cannot be copied easily on paper? The concept seems simple: lasers, optics, power systems, control software. But copying this machine is not about understanding theory. It is about mastering execution. It requires decades of accumulated knowledge, thousands of highly specialized engineers, industrial infrastructure capable of extreme precision, political will to fund long-term non-commercial research, security systems protecting classified designs. Most countries lack at least one of these elements. Many lack all of them. Even with unlimited money, building this machine would take years of trial, failure, and reinvention. That is why only a handful of nations have attempted anything remotely similar, and none at the same scale. The dual nature of the machine: this system exists in a moral gray zone. On one hand, it supports nuclear deterrence, ensuring weapons remain safe and controlled without testing. This arguably reduces the risk of war. On the other hand, it preserves the knowledge needed to build and improve weapons of mass destruction. At the same time, it offers hope. Fusion energy research conducted using this machine could lead to clean, near-limitless power. The same technology that simulates nuclear explosions could one day eliminate the need for fossil fuels. Destruction and creation, powered by the same system. This dual nature is why the machine remains controversial and carefully managed. Security beyond physical walls. Security here is not just guards and fences. Information is compartmentalized. Engineers often work on subsystems without knowing the full picture. Access is limited not by rank, but by necessity. Even internal communications are monitored to prevent leaks. Digital security is just as intense. Control systems are isolated from external networks. Software updates are validated, tested, and approved through multi-layer review processes. The risk of cyber intrusion is taken as seriously as physical sabotage. In this facility, information is treated as a weapon. Why the public rarely hears about it? There is no marketing value here, no commercial product, no consumer benefit that can be advertised. And there is risk. Public attention invites scrutiny. Scrutiny invites debate. Debate invites political interference. For a system this complex, stability is more valuable than publicity. So the machine operates quietly, influencing global security and scientific progress without ever appearing on the evening news. The future this machine controls. By the time this machine reached operational maturity, it had already changed the rules of global power quietly. No announcements were made. No victory speeches were delivered. Yet deep inside scientific and defense communities, one fact became clear. The future would no longer be decided by who had the biggest weapons, but by who understood the most extreme systems. This machine represents a shift in how power is measured. In the past, power meant production capacity, raw materials, or military numbers. In the modern era, power means control over complex systems. Systems so advanced that only a handful of organizations on Earth can even operate them. And America had built one of the most advanced systems ever conceived. The fusion dream at the center of the machine's long-term purpose lies a promise that borders on science fiction: controlled nuclear fusion. Fusion is fundamentally different from fission. Instead of splitting atoms apart, fusion forces atoms together, releasing enormous energy in the process. It is how stars shine. It is clean. It produces minimal waste, and it offers energy densities millions of times greater than fossil fuels. For decades, fusion remained theoretical. Laboratories could achieve fusion reactions for fractions of a second, but never long enough or efficiently enough to produce usable energy. This machine changed that. By recreating the exact conditions required for fusion, extreme temperature, pressure, and confinement, scientists could finally study fusion reactions in controlled experiments. Not simulations, not estimates. Real reactions, measured and analyzed in detail. Each experiment brought humanity closer to answering a question that could redefine civilization. Can we power the world the way stars power the universe? Traditional deterrence relied on the threat of testing and retaliation. Modern deterrence relies on confidence without action. Confidence that systems will work if ever needed, without ever proving it through explosions. This machine provides that confidence. It allows scientists to validate weapon behavior, aging effects, and material degradation without detonating a single bomb. This reduces environmental damage, political tension, and the risk of escalation. In a strange way, the machine makes the world safer by making war less likely, but it also ensures that power remains concentrated in the hands of those who control such systems. Ethical questions. Nitrogen monoxide one can escape with great control comes uncomfortable questions. Should any nation possess the ability to simulate nuclear explosions indefinitely? Should knowledge of extreme physics be restricted? Who decides how such machines are used? There are no easy answers. The same system that prevents nuclear testing also preserves nuclear knowledge. The same research that enables clean energy also improves weapon understanding. Progress and danger are inseparable here. Engineers working on this machine understand that every breakthrough carries responsibility. Many believe transparency is necessary. Others argue secrecy prevents misuse. This tension defines modern engineering ethics. Why this machine symbolizes the 21st century. Unlike the iconic machines of the past, rockets, bombs, factories, this one operates mostly unseen. It does not conquer territory. It does not produce consumer goods. It does not generate profit in the traditional sense. Its value lies in understanding. Understanding forces that once belonged only to nature. Understanding energy at its most fundamental level. Understanding systems so complex that no single mind can grasp them fully. This is the defining characteristic of modern power. Not strength, not speed, but comprehension. What most people never realize, while the public debates visible technologies, phones, cars, social media, the true frontier is invisible. It exists in facilities like this one, where engineers manipulate light, matter, and energy at scales that redefine possibility. Most people will never see this machine. They will never hear it operate. They will never stand near its core. They will never understand its full impact. Yet its influence reaches everywhere, shaping energy research, global security, and the future trajectory of human civilization. The quiet future as this machine continues to evolve. It will become even more powerful. Not necessarily in raw output, but in precision, efficiency, and understanding. Each experiment refines models. Each failure reveals new physics. Each success pushes humanity closer to mastering forces once thought untouchable. The future will not be shaped by loud displays of power. It will be shaped by silent systems like this one, operating in the background, invisible, yet decisive. Why fusion is harder than IT sounds? Fusion is not just about heat. It is about symmetry. The fuel must be compressed evenly from all directions. Any imbalance causes energy to escape, killing the reaction. Achieving this symmetry requires laser timing, precision beyond anything used in commercial technology. It also requires materials capable of surviving radiation levels that destroy ordinary matter. Sensors must function in environments that would instantly disable normal electronics. Diagnostics must capture data from events that exist for billionths of a second. This machine became the only place where all these challenges could be addressed simultaneously, and each solution developed here spilled over into other industries: medical imaging, semiconductor manufacturing, aerospace engineering, and advanced materials science. Even when the machine fails, it pushes technology forward. The global power shift, other nations noticed. Quietly at first and urgently. Countries with advanced scientific programs began investing heavily in similar facilities. Europe, China, and others launched their own large-scale laser and fusion projects. But catching up is not simply a matter of spending money. America's advantage lies in time, decades of accumulated data, thousands of failed experiments turned into knowledge, industrial ecosystems built specifically to support extreme precision. This is not something that can be copied quickly. That gap translates directly into strategic leverage. The nation that masters fusion first will not just control energy, it will control economic stability, industrial growth, and technological leadership for generations. A machine that redefines deterrence beyond energy. The machine plays a silent role in nuclear stability. The silent machine that shapes the world when history looks back at the machines that defined human civilization. It will not remember only the loud ones. It will not remember just rockets lifting off, bombs exploding, or factories churning smoke into the sky. Instead, it will remember the machines that changed how humanity understood power itself. This machine is one of them. It does not conquer land. It does not generate headlines. It does not announce its presence. And yet it quietly decides what is possible and what is not. America did not build this machine to impress the world. It built it to understand forces that once belonged only to nature, to gain control over energy, matter, and physics, at a level where guessing was no longer acceptable. This is what separates modern power from ancient power. Power has evolved in ancient times. Power came from numbers, armies, manpower, territory. In the industrial age, power came from machines, factories, engines, weapons. In the digital age, power came from information, data, networks, computation. But in the 21st century, power comes from systems. Systems that are too complex to explain in a speech. Systems that require decades of investment. Systems that cannot be copied easily even with money. This machine is not powerful because it fires lasers. It is powerful because it represents the ability to design, control, and operate complexity at the highest possible level. Why most countries will never build one. From the outside, this machine looks like an engineering project. From the inside, it is a national philosophy made physical. To build it, a country must be willing to invest for decades without immediate results. Accept failure as part of progress. Coordinate thousands of experts across disciplines. Protect knowledge while still advancing science. Think in generations, not election cycles. Most governments cannot do this, not because they lack intelligence, but because they lack patience. This is why such machines are rare, and why those who possess them quietly shape the future. The machine as a mirror in many ways. This machine reflects the society that built it. It is precise, it is controlled, it is disciplined. Every decision is reviewed. Every failure is analyzed. Every success is measured. There is no room for improvisation at this scale. No room for shortcuts. No tolerance for ego. This is engineering stripped of romance and reduced to reality. And that reality is unforgiving. The future IT enables the machine's greatest contribution may not be nuclear security or fusion research. It may be something far more subtle. It trains a generation of engineers to think differently, to see problems as systems, not objects, to value reliability over speed, to design for failure, not perfection. These engineers take this mindset into other fields: energy, aerospace, medicine, climate science. The influence spreads quietly, shaping technologies most people never connect back to this machine. This is how real change happens. Not through announcements, but through infrastructure, culture, and knowledge. The danger of invisible power, but invisible power comes with risk. When systems become too complex, they become difficult to govern. When knowledge is too concentrated, it becomes tempting to misuse. When machines operate beyond public understanding, accountability becomes fragile. This is the paradox of modern engineering. The tools that protect civilization are often the same tools that could end it. That is why restraint matters as much as capability, and why silence, in this case, may be intentional. Closing the circle at the beginning of this story, we said that the most powerful machine America ever built does not look powerful. Now you understand why. Power today is not about spectacle. It is about control. It is about understanding. It is about systems that operate beyond human intuition. This machine does not dominate through fear. It dominates through knowledge, and knowledge, once achieved, cannot be undone. Final takeaway: the world's future will not be shaped by the machines we see every day. It will be shaped by the machines hidden behind concrete walls, by systems that operate for milliseconds, but influence decades, by engineers who understand that the most dangerous forces are the ones we barely comprehend. This is how America secretly built one of the world's most powerful machines, not to rule the present, but to control the future. If you want to understand how the world truly works, if you're fascinated by hidden megasystems, invisible engineering, and machines that shape civilization, like this video, subscribe to the channel. Comment below, which secret machine or mega project should we uncover next? Because the most important stories are rarely the loudest ones.